Hello everybody, my name is Diana Chavarria. I'm a doctoral researcher at the Center for Wireless Communications, University of Oulu. Here I'm presenting some of the results of our new paper, which is entitled Self-Energy Recycling for Low-Power Reliable Networks, Half-Duplex or Full-Duplex. The paper is open access and was accepted for publication in IEEE Systems Journal. A link to the paper is available in the description of this video. In our work, we focus on ultra-reliable communications, specifically on how to achieve maximum reliability fairness between uplink and downlink transmissions. Notice that we mean here by reliability fairness the possibility of bringing as close as possible the outage probabilities of both uplink and downlink channels. We also analyze the impact on the reliability of the use of self-energy recycling, which allows to reuse part of the transmitted energy by means of an energy loop. To achieve such reliability fairness, we propose a dynamic full-duplex scheme where the antennas can be switched indistinctly between transmission and reception. We also derive an expression for the probability density function of the recycled energy. We derive closed-form expressions for the outage probabilities in both half-duplex and full-duplex modes, with the presence of self-energy recycling. We also determine the optimal antenna configuration for maximum reliability fairness and determine the minimum number of required radio frequency chains for a certain reliability target. Let's consider the following scenario. We have a full duplex small base station where it's receiving data in the uplink and is simultaneously serving a device in the downlink channel. The base station is equipped with a certain number of antennas for transmission, reception, and self-energy recycling. The figure also shows the presence of a self-interference link between transmission and reception. This is because in full duplex mode, the same frequency is used in both directions. To achieve maximum reliability fairness, the main goal here is to minimize the maximum outage probability between both links. For doing so, we are not increasing the transmit power or adding more antennas at the base station side, but only changing the antenna configuration. This is, the base station can change the number of transmit and receive antennas from the total. On the right-hand side, we show our main assumptions. These are quasi-static Rayleigh fairing, maximal ratio transmission and maximal ratio combining at the base station, perfect knowledge of the channel state information, linear mode for the energy recycling, and half-duplex and full-duplex small base stations. In the following, we illustrate some results. The figures show the outage probabilities of both links and the optimal operation points when changing the antenna configuration at the base station side. The optimal operation points, or optimal antenna configurations, are those where the outage probabilities get closer to each other. Notice that there are some difference between both figures. This is because on the left-hand side we didn't consider self-energy recycling, while on the right-hand side we consider 6 antennas for self-energy recycling. The use of self-energy recycling allows to collect more energy and therefore to transmit with more power, which impacts on the optimal antenna configuration. The figure on the left-hand side shows the optimal number of transmit antennas from the total for different rates in both uplink and downlink channels. Notice that the optimal antenna configuration changes when 6 antennas are used for self-energy recycling. The figure in the middle shows a comparison of our proposed full-duplex scheme with classical full-duplex and half-duplex mode. We can clearly see that our proposed method greatly outperforms full-duplex and half-duplex in terms of min-max outage probability. Finally, the figure on the right-hand side shows the minimum number of radio frequency changes for a given min-max outage probability. This information is very important since it allows to save energy by switching off the antennas that are not required. Thank you very much for watching this video from our 5-minute series. For more information on our work, please refer to the link on the description of this video.